This is Mr. Craig, and I want to discuss electrochemistry. I believe this is our first lecture dealing with electrochemistry, and a lot of this is going to have some review. There will be 2 videos for day 125, so let's go ahead and get right into it. The first thing I want to talk about is the review of oxidation and reduction. Do make sure that you know what is happening when something is oxidized and when something is reduced. Do realize that we did talk about this earlier in the year, that if something's being oxidized, then it has a loss of electrons. If something is being reduced, then it's gaining electrons. Also, be sure that you know the oxidation state or the oxidation number for an atom when it becomes part of a compound. Do remember that metals want to have a positive charge, where non-metals want to have a negative charge. And we should be able to identify what the common charge is for an ion. Now, when we look at a periodic table, again, just like with your periodic table, it's not the same as the one that I have here, but you'll notice that there's no markings on the top here, where we don't have any like group 1A, 2A, and 3A, and so forth and so on. What we do care about is knowing what the charge for a potential element is based on if it's a metal or a non-metal and how far away from the noble gases that element actually lies. So when we look at, say, the noble gases, the far column over here on the right, that's what the common charge deals with. So if I'm looking at, say, magnesium, element number 12, and I want to say, okay, well, what's the common charge for magnesium? Well, is it easier to gain 6 electrons, or is it easier to lose 2 electrons? Well, for magnesium and everything in that column, or in group column 2, or the alkali earth metals, it is much easier to lose 2 electrons, therefore magnesium will have a +2 charge. Actually, everything in group 1A wants to have a +1 charge, everything in group 2A wants to have a +3, everything in group 3A wants to have a, everything in group 3A wants to have a +3. Then when we get over to the column here with the carbon, then it gets a little muddy. Those elements want to have either a +4 or a -4 charge, but there's also some other charges that are involved there. So group 4A, you're not going to be held responsible for knowing the common charge. But once we jump over the nitrogen, everything in that column, that is a non-metal, will have a -3 charge, oxygen -2, fluorine -1. So again, it's all about how far away from the noble gases are these elements and the common charge. So you should not have to have those charges on your periodic table to determine what the charge is. Now, when we look at the transition metals, again, the transition metals are our d orbital elements, okay, down here in the d block. Come back here. When we look at the d orbital electrons, the d orbital elements, you don't have to know what the charge is. In other words, you don't have to memorize that. Oh yeah, lead over here, not necessarily a d orbital element, but it has either a +2 or +4 charge. That's a multiple charge metal. You don't have to know that iron has a +1 or a +2. However, you should be able to determine what the charge on the metal is based on the charge of the non-metal. So making sure that you know your 10 polyatomics, and I'll talk about that here very shortly, making sure that you know the common charge for a single non-metal element, and being able to do the algebraic sum to determine what that charge is. Now, don't forget about the aluminum, zinc, silver slide, or I call it the aluminum slide. You must know the charge on zinc, you must know the charge on silver. Get off of there. So remember that aluminum's 3, zinc is +2, silver is +1. So that's the aluminum slide, 3, 2, 1. All the others have multiple charges that we care about. All right, getting back to the notes here. Again, so know your common charge. You'll never need to memorize the possible charges on the transition metals. I'm looking right here, but you should be able to determine the charge or the oxidation number based on the non-metal. All right. Be sure that you know your 10 polyatomics. Again, the 10 polyatomics, and I know some of you, I haven't remembered that in a while. Remember them. You need to know these 10 polyatomics. Also, make sure that you know if I gain an oxygen or lose 2 oxygens, how to name those polyatomics. Very important, guys, now that we're getting close to the AP exam. Let's see here. Oxidation reactions are also known as redox reactions. We did this very, very early on in the year. If you don't remember how to do a redox reaction, be sure that you go back and review that. You will see that on the multiple choice portion of the AP exam. However, what we're doing today is, quote-unquote, very simple redox. In other words, I want to find out when we look at a reaction here, what's going on, and I know it says a very common redox example or a demo, and I'll show that when I get back, is where we take an iron nail and we put it in a solution of, in this case, copper sulfate, copper 2 sulfate. And what's happening is that the iron metal is actually replacing the copper in the solution, and we actually see the formation of solid copper on this iron nail. You'll see that when we get back here. And then the iron that was once a solid now becomes aqueous, and it changes the color of the solution from this beautiful aqua blue to kind of a dark grungy color. So it's not a very pretty reaction, but we do have a single replacement. And when we talk about a redox reaction, it is a single replacement reaction most often. And what's actually happening in this reaction? An oxidation reaction is taking place as well as a reduction reaction. The iron, which has no charge, is losing 2 electrons and becoming a +2 charge. However, the copper that has a +2 charge is gaining electrons. Notice that the electrons are on the same side as the ion itself, or on the left side. So it's gaining 2 electrons and becoming neutral. In other words, it's becoming more negative, even though the element itself is not negative. So when we talk about a reduction, we're talking about a gaining of electrons, where oxidation is a loss of electrons. And that's what this little saying here is. So when we talk about whether something's gaining or losing electrons, I like to use, Leo says GER, but you can also talk about oil rig. So oil rig. And if we talk about oil rig, it's oxidation is losing, where reduction is gaining. Not a big fan of oil rig, but hey, whatever works for you is fine by me. Oxidizing agents and reducing agents. Let's take a refresher on that. Remember, when we talk about agents, number 1, they must be on the reactant side. Also, the agents do the opposite, or they have the opposite name of what they're doing. So in other words, the iron in our example here is being oxidized. Therefore, it's allowing the copper to be reduced. Therefore, the solid iron is our reducing agent because it is oxidized. When I look at the copper +2 metal, or whatever comes with the copper +2, the agent is the whole package. So if I told you that we had copper sulfate would be the agent. But what's happening is copper is being reduced and allowing iron metal to be oxidized. Therefore, the iron +2 is the oxidizing agent because it is reduced. So the agent allows the other thing to take place. All right. So again, that's where the agents are at. Let's see. Let's turn the page over to the back side here. Electrochemistry. That's what we're doing right now. It's the study of the interchange of chemical and electrical energy. And this is what we do for batteries, for other types of reactions that take place for single replacement reactions. It's an interchange of chemical and electrical energy, which is kind of cool. We're primarily concerned with 2 processes, oxidation and reduction reactions, and the generation of an electrical current from a spontaneous reaction. And the key here is, we've already talked about spontaneity. If the reaction takes place on its own, we don't have to do anything except place them in the substance that they're going to react within. This is a spontaneous action. And we'll talk about whether something is spontaneous or not here in a few minutes. All right, so reduction potentials. Finally, if you take your periodic table out, go ahead and take your periodic table out and take a look at it. Except I want you to flip the periodic table over and look at the back side. And you should see a table that looks something like this. It says standard reduction potentials in an aqueous solution at 25 degrees. Okay, that's what I want us to look at. This is the first time we've actually looked at this information. But these are standard reduction potentials. Notice that everything on the left side is a reduction reaction, or it's being reduced. Okay, back in the day they used to have oxidation or standard oxidation potentials where they had the reactions flipped and the whole table was inverted. So fluorine, which is on top here, is actually on the bottom on a reduction, but we don't need to worry about that. What I do want you to realize is the voltage, this column over on the right here, where it talks about the voltage here, and we have positive voltages up on top and we have negative voltages near the bottom. And notice that lithium has a negative voltage when we talk about lithium ions going to lithium solid by gaining 1 electron. So that's going to have some significance here. And notice that we have nonmetals up here, actually the fluorine, the bromine, let's see, there should be another one up here. I thought chlorine, there's chlorine. Okay, so you have fluorine, chlorine, bromine, and iodine should be, there it is, iodine's down here. So we have our nonmetals that like to be oxidized. And then there's a few other elements on here that, and you'll notice that they're ions that actually like to be reduced as well. So we'll come back to that table here in a moment. All right, so when we talk about reduction potentials, we looked at our sheet and we saw that for, I have my first example here where lithium, the lithium here has a reduction potential of a negative 3.05. However, if the lithium is being oxidized, which lithium loves to be oxidized, it has a voltage with a positive voltage. Now, you're going to find out real quickly here that reactions that are spontaneous want to have a positive voltage. In other words, they want to generate a voltage. And I would dare say that if we look at your cell phone battery, what kind of battery do you have? I'd be willing to bet that you have a lithium-ion battery. Because what happens, solid lithium, which we can package very easily, is able to change into lithium ions and give us a very high voltage. So when we look at our standard reduction potential sheet, that's why we use lithium batteries, because it's right down here. It gives us the most bang for our buck. Back in the day, they used to use nickel-cadmium. Nickel and cadmium are a little higher up, and we didn't have the technology to make better batteries as we do now. So that's why we use lithium. Okay, so we'll come back to that. Let's clear that off. Oops, clear everybody, guys. All right, so the standard reduction potential. If it's a reduction reaction, then we're going to use the values that are on the table. If it's an oxidation reaction, we simply flip the reaction and flip the sign. Nothing wrong with that. We can do that. All right. You can calculate the potential, and I'm right here, you can calculate the potential of a redox reaction if you know the potentials for the two half reactions that actually make it up. There are two important things to remember when calculating the potentials of a redox reaction. Add the potential for the oxidation half reaction to the potential of the reduction half reaction. And the most important line on here, number 2, we never ever multiply the reduction potentials. In other words, say that if I have lithium that we know has a +1 charge, and say that we're reacting that with aluminum that has a +3 charge, we know that we have to multiply the lithium by 3. We do not multiply the voltage by 3. We just simply add up the potentials, and if we get a positive voltage, this is going to happen. If we get a negative voltage, it is non-spontaneous. So again, simply add the potentials and then never ever multiply the potentials based on how many times we have to multiply it. So it's not like Hess's law where, okay, I have to multiply this equation by 3 to balance it out, therefore I'm going to multiply the delta H's. Not doing that with this. All right. Let's see here. Since iron is being oxidized, we find the reduction for the iron 2, and again, this information is on your chart. Since it looks like here, this is an oxidation, it'll have a positive voltage, and I'm looking at this example up here, I apologize. So this is our iron nail going to iron ions, and again, we don't have any oxidation reactions on our standard reduction potential sheet, so we have to flip the equation, therefore flipping the sign. We know that the copper +2 is being reduced. luckily it has a positive voltage, so when we add these two voltages together, we get a positive voltage. So did this reaction happen? Well, I plan on showing it to you when I get back, so the answer is yes, and it is spontaneous. So a positive voltage gives us a spontaneous reaction. Now, the equation that we're using to calculate this, again, going back to delta G, we talked about it in kinetics, is if delta G, the free energy, has a negative sign. Delta G is negative. If delta G is negative, this reaction is spontaneous. And again, spontaneous in the forward direction. So forward means, yes, we're taking reactants and forming products. So the only way that that's going to happen is if we have a positive voltage. If I have a negative voltage, then that negative sign actually changes that voltage into a positive value, which makes delta G positive. All right. Now, what are these other two values here? The N and the little funny looking F here. Okay. That's actually a sign for Faraday's constant. And Faraday's constant is on your equation sheet. Excuse me, and it's equal to 96,500 joule volts, or joules per volt. And that actually is equal to a coulomb per mole of electrons. We'll use that equation actually in the next set of examples when we do the math. The N represents how many electrons are actually exchanged. So if we have, say, in our example up here, we have 2 electrons here, and where's the other reaction? 2 electrons here. So we have an exchange of 2 total electrons. The copper absorbs 2 electrons while the iron is losing 2 electrons. So the example where I gave with the aluminum and the lithium, okay, my pen's not working very well, but aluminum would have a +3 charge, the lithium would have a +1 charge, so it would be a total exchange of 3 electrons when we do a calculation like that. Again, if delta E is negative, that means delta G will be positive. That means the reaction will not be spontaneous in the forward reaction. And if we have delta G that is negative because our voltage is positive, then we have a reaction that will be spontaneous. All right. I think that's it for this example sheet. Go ahead and view the second video.